Okay, now this section kind of ties together some things we've been looking at in previous sections, so I'm going to go back and do a short review. We talked about inner product, and inner product is an operation between vectors. So here you see u and v, and the inner product is defined in this funny way. And we did mention that inner product is similar to scalar product that you may have seen in physics. There's this formula you may have seen in physics, is that v dot w is equal to the length of v times the length of w times cosine of theta, where theta is the angle between the two vectors. So if you've got two vectors like this, then the inner product is the length of one vector times the length of one vector times the cosine of the angle between them. Okay, so you can think in some sense that inner product defines a notion of angle between vectors. Now, in this chapter, we don't write inner product with a dot. We write it with these angle brackets, and we use complex numbers, but still in some sense, inner product is used to define an angle between vectors. Now, notice when you have two vectors at 90 degrees, if you remember your trig, that's a 90-degree angle, then the cosine of 90 degrees is 0. So it's possible to have an inner product of 0 between non-zero vectors. Okay, and that's called orthogonal. Two vectors have a 0 inner product, that's called orthogonal. Okay. Now, we also related inner product to the norm or length of vectors, that the inner product of a vector with itself is called the norm or length squared. Now notice that a vector can never be perpendicular to itself, can never be 90 degrees to itself. So in fact, the length is never 0. But as we mentioned in this section, it's possible to have non-zero vectors whose inner product is 0. Now it turns out that orthogonal vectors, vectors that have inner product 0, have some very, very nice properties. First of all, they're linearly independent. And now we're going to use these orthogonal, we're going to show that you can take any old set of vectors and use them to create a set of orthogonal vectors. Okay, so, and we'll see how useful this is later on, that it's nice to have sets of orthogonal vectors. Okay, so let me just go over the statement of this theorem, and we'll do an example. I'm not actually going to go through the theorem. It's kind of complicated. It's better, I think, to do an example. All right, so here's the statement of this theorem. Suppose you have p vectors that are linearly independent, and we're going to define another set of vectors that we're going to generate using a process. And this is an inductive process. In other words, you start out with all of these v's, you create u1, u2, u3 successively. So from these vectors v1 up to vp, I'm going to create a new set of vectors u1 up to up that are orthogonal and have the same span as the original set. Okay, now I'm sure that that's kind of confusing, so let's just go straight to the example. All right, suppose I have 3 complex vectors given by these 3 vectors. Right. Now, there is a process involved in generating these new vectors u from v, and I'm going to see if we can follow the process. The process is given by this prescription here. All right, it's up here, it's also here. So let's see if we can understand how to use this prescription to find u1. Okay, so this is an exercise in reading equations. This equation looks quite complicated, but the point is you want to read this equation to show how to generate the u's. All right. So if I want to find u1, I'm looking at the case p equals 1. So that's what I'm looking at now, if p equals 1. All right, so let's cut to the chase here. We have all these complicated terms. The last term here is up minus 1. Now, if p is equal to 1, then p minus 1 is 0. Now, there is no u0. So what does that mean? That means that all of these terms with u's don't appear, and the only thing that I have is this first term, v. So that gives me that u1 equals v1. From this prescription, that gives me u1 is equal to v1. And if we go back down to the example on the next page, we'll see that that's the prescription that was used. u1 is equal to v1. All right, now let's see if we can get to u2. Let me just clean this up a little bit. All right, so now we're looking at p equal to 2. And we're applying this equation for p equal to 2. Well, if p equals 2, then if I think about all these terms, the last term that I'm allowed to include is up minus 1. P minus 1 is 1. So the last term is u1. Okay. So what that means is I only take the terms up to u1, and I ignore the rest. For p equals 2, I only take the first two terms. Okay? And that's the formula that we have down here. You see? We've only taken the first two terms. Now, how do you compute these terms? Well, we have a method for computing this inner product, u1, v2. And u1 is from here, and v2 is from the original set. Okay, so I could compute the inner product of u1 and v2. Remember that it's going to be the complex conjugate of 1 times minus I, plus the complex conjugate of 1 plus I times 1, plus the complex conjugate of 1 times 1 plus I. If you do that, you'll end up with well, let's go ahead and do it. We're going to get minus I plus 1 minus I plus 1 plus I. So that gives me the numerator here. That's equal to u1 v2. And if we want to get u1, u1, that would be the same thing as taking 1 times 1 plus, then I have to take 1 plus I times 1 minus I plus 1 times 1. So that's u1, u1. All right, let's see what we get here. If I take u1, v2, if I add all these together, the real part is going to be 2. So here, so if I'm doing this, this is going to be 2. And then the, let's see, the imaginary part is minus I plus I, so that's 2 minus I. Okay, and the bottom part here I have 1 plus I times 1 minus I. If you work that out, that turns out to be 2. So this bottom part is going to be 4. All right, so this ratio turns out to be 2 minus I over 4, and that's times u1. So I have u1 is 1, 1 plus I, and 1. Right. So that's what this part is. Now I need to subtract that from v2. And v2 is up here. All right, so I'm running out of room here. I won't do the arithmetic, but hopefully you can see how to do the computations. You compute the inner products one by one, you form the scalar, multiply the vector, and then you have to add the vectors together. So that's my procedure for finding u2. All right, now how can I find u3? Well, let's go back to our prescription and see how this works. Now this is all messed up, so let me use the same prescription down here. I want p equal to 3 now. Okay, so how far out do I go? Well, since p is equal to 3, my last term is going to be u2. So what does that mean? That means I only take the first 3 terms and I compute these 3 terms. All right, and that's what's done down here in this example. To find u3, there's 1, 2, 3 terms. Again, this is a lot of computation, but you can use technology to compute these inner products. And you'll get vector minus another constant times vector minus constant times vector, and this turns out to be the answer. Okay, so then this is your final result. u1, u2, u3 turns out to be an orthogonal set that has the same span as the original set. Okay, so that's a very nice procedure. All right, now there's one further thing we can do to this orthogonal set. We can change this orthogonal set so actually the norm of each vector is equal to 1, and that's called an orthonormal set of vectors, and that's really the gold standard as far as linearly independent sets go. Right? So how do you create an orthonormal set of vectors? Well, in our last example, we created an orthogonal set of vectors. These are already orthogonal, means the inner product of any two is 0. The only thing that remains is to make sure that each vector has a norm equal to 1. Now, to do that, you can just divide by the norm. Okay, for instance, this first vector here, 1, 1 plus I1. If we compute the norm of this, so let's compute the norm of u1. Well, first you compute the norm of u1 squared. That's the inner product of u1 with itself. If you remember how to compute inner product, that's going to be 1 times 1 plus the second term is going to be the complex conjugate of 1 plus 1, 1 plus I, which is 1 minus I, times 1 plus I. And then the last term is also going to be plus 1 times 1. That whole thing gives me 4. Right. So u1 squared is equal to 4. That gives me u1 is equal to 2. Right. Let me do one more example of a norm. If you do this one here, the norm of u2, well, if I was going to do the norm of u2 squared, okay, I have to do the inner product. Now this 1/4 actually is going to distribute into all of these, so it's going to be minus 2 plus 3i over 4 times minus 2 minus 3i over 4 is the first term. Then I have plus. Now when I do the second term in the inner product of u with itself, it's going to be 1 plus I over 4 times 1 minus I over 4. And then the third term is going to be plus, I'm going to have to do it down here, 2 minus 5i over 4 times 2 plus 5i over 4. Okay, if you work this all out, you're going to get this result. One thing you can notice is that the 4s you could just take out. You have a denominator of 16, and then you can work out all of these numerators. One thing that's useful to use is that if you have a case of a minus bi times a plus bi, whenever you have this type of product, the result, and you can work this out, is a squared plus b squared. Okay, so I can actually work this out quite easily. The denominator, I'm going to have to go over here. The denominator is 16. The first term is going to be 2 squared plus 3 squared. So that's going to be 4 plus 9, or 13. Second term is going to be 1 squared plus 1 squared. And that's 2. The last term is going to be 4 plus 25, or 29. Okay. All right, so if you add all this together, we're going to get, looks like it's 44. So I have 44 over 16. And you can see 4's cancel, so that's the same as 11 over 4. And you can verify that the square root of 11 over 4 is a square root of 11 over 2. Remember here I computed the norm of u2 square. Okay. All right, so we can compute this second norm, and I won't do this, but you can compute the third norm in the very same way. So in order to change these orthogonal vectors into orthonormal vectors, all I need to do is divide the first vector by its norm, divide the second vector by its norm, and divide the third vector by its norm. Okay? So that's exactly what's done here. This is first number, divide by the norm 2, second number, divide by the norm square root of 11 over 2, third vector, divide by the norm. Okay. Let's look at another example. Okay, well, you can, all right, so this is just an exercise, but you can see the procedure, and that's how it works.